Hello everyone. I'm honored to have been invited to speak at this conference. My topic is compressed sensing joint image reconstruction based on multiple measurement vectors. I'd like to share with you some of our interesting research on compressed sensing. The content of this presentation is divided into 5 parts. Firstly, we have an introduction of compressed sensing in section 1 and describes the basic principle of compressed sensing in section 2. And then in section 3, the proposed method is given. At last, based on some simulation results, we make a brief summary in sections 4 and section 5. Compressed sensing is a new framework for simultaneous sampling and compression of signals. Compressed sensing explores the sparsity of an unknown signal to recover the signal from much fewer linear measurements. The fact that compressed sensing requires very few measurements makes it very useful to reduce sensing cost in a variety of applications. Signal reconstruction algorithm is the key to compressed sensing theory. Presently, many reconstruction algorithms have been proposed, such as orthogonal matching pursuit algorithm, the basis pursuit algorithm, and the hybrid simulated annealing thresholding algorithm. However, all these reconstruction algorithms for compressed sensing are based on the sparsity of original signal. In order to make full use of the correlation between different image signals, some researchers have presented the relevant reconstruction methods. However, these methods either require estimating the relative camera position or do not perform the reconstruction simultaneously. To date, how to improve the accuracy of reconstruction image while using the correlation between different image signals remains a critical problem. In order to improve the quality of the reconstructed image for compressed sensing, a novel compressed sensing joint image reconstruction method based on multiple measurement vectors is put forward in this paper. Compressed sensing is a technique for finding sparse solutions to undetermined linear systems. This method takes advantage of the sparse nature of the signal and is able to reconstruct the entire desirable signal from fewer measurements than Nyquist theory. The basic idea of compressed sensing is that any sparse or compressible signal can be projected from high-dimensional space into low-dimensional space via linear measurement processing, and then the original signal can be reconstructed by solving an optimization problem. Premise condition of compressed sensing is that the signal is sparse or compressible, but the actual signal usually cannot meet this condition. To solve this problem, the orthogonal transformation processing can be performed. For such a signal without sparse properties, this is the processing process of compressed sensing. Consider a real-valued finite-length, one-dimensional discrete time signal x with the length of n. The signal can be represented sparsely as the first formula. Compressed sensing samples signal by directly acquiring a compressed signal representation without go through the intermediate stage of acquiring n samples. Consider a general linear measurement process that competes n inner products between x, a collection of vectors. The measurement process can be expressed as the second formula. Since m is less than n, the equation appears air-conditioned. However, alpha is a k-sparse vector, and then the problem can be solved provided m is equal or greater than k. The most direct way to reconstruct is by solving optimization problem on the L-line norm as the third formula. Any nature image signal can be orthogonal transformed, and the transposed matrix can be expressed as the first formula in left-hand column. In previous research of compressive image, most scholars will convert the two-dimensional image signal into one-dimensional signal when processed image signal, which means that a long one-dimensional signal is processed under the single measurement vector mode. In this way, the scale of the measurement matrix would be very big, which will increase the amount of calculation and lead to a very long processing time. In order to reduce the scale of the measurement matrix and improve the accuracy of reconstruction, each column of the image signal can be individually treated as one-dimensional signal, and p measurement vectors can be obtained by the same measurement matrix, which means that the two-dimensional image signal is processed under the multiple measurement vectors mode. We assume that the original signal is processed on the MMV mode and random measured by two compressive image camera in vertical and horizontal direction, and then random linear measured by a random matrix. This linear measurement process can be described as the second formula and the third formula. To reconstruct the original signal x with the measurement vectors, the most direct way is by solving two optimization problems on the L-line norm. Here we can get two image-by-image reconstruction images. Reconstruction images would be the same in the case of exact reconstruction, but the error would be introduced in actual measurement and calculation, which would lead to certain differences. In order to improve the quality of the reconstruction image, we advocate the mean of these two view image signals to capture the correlation between them. So the joint reconstruction image is calculated as the third formula in the right-hand column. In order to verify the compressed sensing joint image reconstruction method presented in this paper, simulation experiments are carried out to 4 standard test images. Considering the fast calculation and high accuracy of OMP algorithm in compressed sensing signal reconstruction, the comparison experiments were conducted with single measurement vector OMP algorithm in, MMV OMP algorithm in, and the method in this paper. The original image simulation experiment results of SMV OMP algorithm, MMV OMP algorithm, and the method in this paper are illustrated. From the reconstruction results, we can see that the image acuity and visual effect of the proposed joint reconstruction image is much better than that of the SMV OMP reconstructed image and MMV OMP reconstructed image, which verifies the effectiveness of the proposed method. In order to evaluate the performance of these algorithms, peak signal to noise rate is used as the index of the image reconstruction algorithm. PSNR is generally used for an engineering project between the maximum signal and the background noise. The PSNR shows the difference degree between the reconstructed image and the original image. Table 1 shows PSNR of the simulation experiment results with different sampling rates. From Table 1, it can be seen that the reconstruction's qualities of all algorithms is improved with the increase of sampling rate, and we can conclude that under the same simulation conditions, the joint reconstruction images in this method provide higher PSNR than the images reconstructed by SMV OMP algorithms and MMV OMP algorithms. For the range of sampling rate is large, the experiment also can verify the robustness of the method. Figure shows the PSNR comparison chart of image under the condition of different sampling rate. It can be seen that the PSNR of the joint reconstruction image in this method provide higher PSNR than the images reconstructed by the other two algorithms under the same sampling rate, and the performance of this method does not appear larger fluctuations. It maintains a good stability with the change of sampling rate, so it is an effective compressive image method. A novel compressed sensing joint image reconstruction method based on multiple measurement vectors is put forward in this paper. We assume that the original image is processed under the multiple measurement vectors mode and random measured by two compressive image cameras in vertical and horizontal direction. After these two different sampling direction images are reconstructed, the mean image is used to capture the correlation between them, and the original image is joint reconstructed. The experiment results showed that the accuracy and visual effect of the joint reconstruction image by this method are much better than the reconstruction result by SMV-OMP algorithm and MMV-OMP algorithm, and the performance of this method does not appear large fluctuations with the change of sampling rate, so it is an effective compressed sensing joint image reconstruction method. Thank you for watching.